scare us with some geology stuff. Thank you.
We should order it in like height. That way we don't have to do this adjustment every time. We've gone to the opposite end of the spectrum. Thanks, everyone. This is actually a picture from probably 2019, maybe was the last time we were here, George. So this is my third time in Venice for this conference, and it stuns me every time. It's in fact difficult to give this talk and concentrate on it and not let my eyes drift out the window. It's a great place to come, and I really appreciate the invitation to return. Yeah, we're going to pattern this session kind of, or at least this early part of it kind of building up, and I'll talk a lot about the geologic characterization that we collected. That supports the Class 6 permitting and the modeling that's associated with that George Caperna, also with ARI, will present on. And then Catherine Dombrowski will talk to us about how to actually get the CO2 from the plant to the wellheads, to the injection wells. So kind of a holistic collection of presentations, at least from the outlet of the capture unit through the subsurface and the permitting and monitoring throughout. I'm Dave Riestenberg with Advanced Resources International. I'm a geologist. I lead a team of smart geologists and geoscientists on CCS projects like this. Work very closely with George Caperna, who will present next. He's our senior engineer, and together, we kind of meet in the middle and put together CO2 storage permits now in the U.S. And as Richard mentioned, that's big business for us. Probably in 2019 and earlier, we would have said we've got a handful of these projects. They're all DOE funded. Well, now there's still a lot of U.S. Department of Energy funded projects, a lot of private money investing in this as well. And, in no small part due to, obviously, the tax credit that's out there that Richard spoke on. But also, a lot of the confidence that's these types of projects that we're able to present on because the federal government in the U.S. supports them has helped the industry build confidence in this technology. Patty already gave the disclaimer, thankfully. Hopefully everyone read it. DOE takes no, they do not advocate, well, they may advocate, but they don't take liability for anything I may misstate. This is the third time you've seen a slide of the southeastern U.S., so hopefully everyone can remember which order Mississippi and Alabama fall in the U.S. It took me about 20 years to figure that out. But our project is in the starred area, which is in Mississippi, so the southeastern U.S., hot, hilly, humid, swampy, wooded, kind of a difficult terrain to work, unless you like heat and you like mosquitoes. But the storage geology is really nice there. And we're operating under the U.S. DOE's Carbon Safe program. And that was a DOE initiative started 6 or 7 years ago to try to promote commercial CO2 storage sites in the United States. And their definition of commercial was sites that could store safely and securely 50 million metric tons of CO2 in 30 years of injection. So let's say 1.7 million metric tons per year. If you follow the press in the U.S., it's almost like projects in commercial sense have moved beyond that. You hear projects 5 million metric tons a year. But when this initiative came out, that was a huge number. And so we're one of, I think, 4 projects that are at this phase, this third phase in the program that Patty mentioned, and there's a whole lot of projects following us up, probably a dozen or more, and DOE continues to put out funding opportunities for carbon safe projects. And again, they're phased. You pick them up from a kind of a pre-characterization phase and move them all the way up. None of them have reached this point, but a 4th phase in the program, which would be commercial build-out, drilling of your injection wells. So DOE would provide support with industry cost share. I'm pointing at Richard because he's telling me he'll get it for us, for all the way through commercial build-up, so drilling of your injection wells, installing your CO2 distribution lines, et cetera. So a very supportive program from DOE. And then, kind of the overall objective of this project is to, evaluate commercial prospects for CO2 storage in the southeastern U.S. Richard mentioned that Southern Company is one of the 2 or maybe 3 biggest utilities in terms of generation in the United States. They're only one of many, many, many point sources of CO2 in the southeastern U.S. It's very industry heavy, particularly along the Gulf Coast. So there's a lot of CO2 storage sources out there. In fact, I think all the dots on the map are CO2 sources, and they're sized by CO2 emissions volumes. Patty mentioned the partners. We could do a session on this project, ECOS, and probably take 2 or 3 days if we gave everyone enough time to present, at least at a cursory level, everything they're doing. But there's universities, private companies, vendors, lawyers even, I was pointing the wrong way, lawyers even, you know, other parts of the federal government, like United States Geologic Survey, that are helping us build this story of CCS at this particular site. Well, again, I'll talk about the geologic data acquisition and characterization. I think Patty may have showed a slide similar to this, but between the two phases of the project, we've actually drilled 6 characterization wells. Interestingly, 4 of those we drilled and preserved in a situation that they could serve as monitoring wells for a CO2 storage project, should that take place going forward. So we haven't drilled any injectors yet, if that question sometimes pops up in people's heads, but we've drilled wells that could serve as monitoring wells in the future. We've pulled a lot of logs from every single well, cored a number of them, and so we have whole core from both reservoir rock and confining unit rock, run a suite of tests on those to determine not only the storage characteristics of those reservoirs, but the confining characteristics of the overlying confining units, but also those baffles or zones that are within the injection reservoirs and between them that'll serve to segregate the CO2 plume vertically. And then we also collected a grid, I guess you'll call it, of 2D seismic lines, about 90 miles of 2D seismic. The question typically comes up, you know, why didn't we collect a 3D seismic survey? A couple reasons for that. One, pragmatically, you know, we're characterizing a relatively large area here, you know, 10, 20,000 acres. So, you know, let's say 4,000 to 8,000 hectares if you think in those units. That would be a really, under the budget constraints of this project, pretty difficult to collect a 3D seismic survey over that large of an area. But also realistically, again, I mentioned this is hilly terrain and very swampy in the valleys. It would be exceedingly difficult to collect a 3D seismic survey. And so I mention that because it's important in terms of our monitoring plan. A lot of folks, I'm sure you guys are familiar with the CCS industry to know 4D seismic or repeat 3D seismic is a really commonly proposed CO2 monitoring technology. Well, we're not proposing that as a CO2 monitoring technology here. I think George will describe our monitoring program in terms of regulatory compliance in the next presentation, but ours is largely well-based. And the last thing I'll say about, you know, the number of wells that we've drilled here, we're kind of in a sweet zone in terms of depth of the formations here. So we're onshore. That makes drilling a lot cheaper, obviously, than offshore. But our reservoirs are in the 4,000 to 6,000 foot deep range. Gets us deep enough that we have sufficient pressure for supercritical storage, but it's not so deep that these wells are going to cost tens of millions of dollars to drill. So, you know, we can install wells relatively inexpensively, so we really leaned heavily on a well-based characterization program. What was the term, kitty cat? Fat cat kitty storage geology in terms of a stratigraphic chart here. So this is really good storage geology in terms of net pay of your reservoirs for storage. We've got 3 of them moving from deepest to shallowest. Maybe hard to see there, but the deepest one that has, you know, it's kind of serrated in the log pattern with a lot of tannin there. That's indicating sandstones. The deepest one's the Paluxy at, you know, 5,000 feet. And then shallower than that, you've got the Washita-Fredericksburg interval, a lot of sand, again, albeit segregated by some of those internal confining units that'll effectively act to distribute the CO2 vertically. And then also the lower Tuscaloosa massive sand, that's at 3,500 feet. So a lot of storage geology there. In fact, you know, it's over 1,000 feet. Yeah, we even put meters in there, 400 meters of CO2 storage reservoirs. And these are mean porosities in the 28% range, permeabilities in the Darcy range. In fact, it's poorly consolidated sand. If you don't core it correctly, you pour it out, sand out of the core barrel. It's a very sad moment for a geologist, but for our storage engineers, they delight in seeing things like that. Conversely, the mud rocks that are seals, I'll show a slide in a moment, but they're very tight. This is a system that's relatively immature geologically, and by that I mean it hasn't seen a lot of compaction. It hasn't seen a lot of stacking of geologic units and then later erosion like you have in a lot of parts of the U.S. Like when Richard mentioned that valley and ridge region with his that cool sand model, that's had mountains built up on top of it. That's really cooked and compacted those rocks, and then that's eroded away. These rocks were never buried particularly deeply, and that's interesting in terms of those confining units. because those mud rocks are still hydrated. So they have low permeability by nature, and they also are very ductile. And just remember, in terms of CCS, maybe this is old news to everyone here, ductile rocks is great, right? If anyone's worked in the oil and gas industry, maybe this is US-centric, we look for brittle shales for tight oil and for gas shales because we can hydraulically fracture them, right? And those fractures might stay open. But for CCS, we like rocks that are ductile, that, you know, they have a higher fracture pressure, but even if we did exceed that fracture pressure, they'll heal once we drop the pressure back down. So it's a good setting, both in terms of reservoir and also in terms of confinement. And then, you know, if you add up how much pore volume you have there, multiply it by your area, and apply some sort of storage efficiency or risking to it, you know, what we're finding is you could potentially have 20 million metric tons per square mile, or in this 30,000 acre storage complex, you may be able to store a gigaton of CO2. So, which actually is in far in excess of probably what Plant Ratcliffe, which is right at our site, could supply. So this could be a regional storage site in terms of subsurface geology. Just a word about those confining units. This is some good work that our partners from Oklahoma State University did. Yeah, I think maybe I mentioned everything in the slide, but you know, they've been interpreted as tidal flat deposits. So these are not marine shales that most folks are probably used to seeing. Our storage reservoirs are fluvial sands, and our you know, our confining units are tidal flat deposits. So probably geologists in the crowd are probably thinking, well, that's cool, but I'm kind of worried about lateral continuity, right? Because I don't think of these things as miles long continuous settings like you would a marine shale. So there's another argument for collecting seismic and drilling multiple wells that we can collect a lot of core to be sure that you've got this lateral continuity of reservoir and confining unit. Structural risk here, or maybe interesting structures, are pretty low in this part of the world, which is great for CO2 storage. Our seismic folks find it very boring interpreting the seismic. Our storage reservoirs, again, are the Paluxy, the Washita Fredericksburg, and the Tuscaloosa, and you have kind of what seismic interpreters in the U.S. would call kind of railroad track seismic wiggles. There's no discontinuities there that would indicate large-scale stratigraphic changes. More importantly, we don't see any fracture zones or fault zones. We don't see wiggles at any of these unconformity surfaces that would make us worry that we've got faults in the system. Faults aren't necessarily a negative for CO2 storage. I know that there's going to be some presentations at the conference about it, but an absence of faults, I think, is always a good thing for us. And again, we collected almost 100 miles of seismic and didn't see any faults in any of those lines. In fact, the geologic structure, if you look at the structure map, the colored map on the upper right, it's showing that dip is to the southwest. It's actually at less than a degree. So that's kind of another interesting point. We don't have a structural trap in a conventional sense in oil and gas, or if there is such a thing as a conventional CCS trap. So our CO2 will be ejected. It'll migrate up dip slowly. George, I think, will present a slide or two on this. And the trapping mechanisms are you know, pore trapping, and dissolution, and long way down the road you'll have mineralization. But we have so much reservoir there, and that discretation of the reservoir vertically will encourage migration of the CO2, excuse me, in the pores and with the pore waters, and it'll encourage trapping. Reservoir lateral continuity and confining unit lateral continuity is played out in this slide. It's a shaded gamma ray slide, so you know the tans of the sandstones, and the darker colors would be your mudstones or your internal and above zone confining units. And so across this storage site, and if I put some old logs that were gathered from exploratory wells in the region on the left and right, you'd see it continues out. So you know, one of the questions I think that comes up in CO2 storage is, yeah, that's great, you've got a lot of pore volume here, but you know, what are your edge conditions like? What are your boundary conditions like? There's not another storage site that I know of that's being permitted nearby Kemper County, but we keep splashing this fat kitty cat storage potential into the region, and so there's no telling that someday someone may permit another site next to ours. And you know, so there could be pressure buildup impacts. This is an issue in the US, believe it or not. You have so many permits being applied for on the Gulf Coast further south that there's worries about pressure buildup. And so, understanding where the reservoirs go laterally, even beyond our storage site, is important. Groundwater characterization. So again, George will present on the permitting for the project, but that comes out of the EPA's Office of Water Protection. So the whole, you've heard the term UIC already, UIC Class 6, underground injection control. That permitting rules are designed primarily not to keep CO2 from being re-emitted into the atmosphere. Its primary driver is to keep from impacts to underground sources of drinking water. And so characterization of groundwater, protection of underground sources of drinking water, or USDWs as EPA calls them, is paramount to getting the license to operate a site like this. And it's not as easy a question as it may initially come out. In the U.S., we're in a lightly populated area, but there's populations, and a lot of folks have water wells. And so you might think initially, well, we'll just go out and survey the depths of everyone's water well, look at a geologic strat column, and we'll say, okay, they're producing their water from this reservoir. We just need to make sure we protect that reservoir. But in fact, U.S. EPA imposes a total dissolved solid standard to what they call an underground source of drinking water. So it's not what the dominant underground source of drinking water is that the neighborhood uses. It's whatever meets this criteria, which is 10,000 milligrams per liter. And most people wouldn't use water that's that salty. Maybe in Venice they do, but in the southeastern U.S., that would be nasty water. You wouldn't even use it for irrigation or anything like that. So a lot of times you have to just drill a well or do special characterization on your deep characterization well to understand what that USDW may be. And in fact, for our project, we had to drill a 2,200 foot deep well to get to the deepest underground source of drinking water. So that's pretty stunning to me that we're gonna have to protect a reservoir that's that deep. We're in a very rainy, wet part of the world. Generally speaking, there's not a shortage of water here. And so I don't think in my lifetime or anyone's lifetime in this room, people are gonna be drilling 2,000 foot deep wells here to produce water, but we need to protect it per EPA rules. But a note on that, it's not as simple to produce water from a 2,200 foot deep well in a repeatable fashion and get the same result. We wanted to have United States Geologic Survey come present to the meeting, but unfortunately they couldn't travel over here for it, which is nice because that means I get to, but I do get to present a little bit on their behalf and the folks that are doing the groundwater sampling, some pretty disparate results that we're trying to currently reconcile. So we drilled this 2,000 foot deep characterization well, installed a screened interval, so a metal screen down there, and then grouted it and cemented up to ground surface, and then produced a lot of water out of it using an airlift. So basically, they put tubing down there, they're injecting air, and the bubbles are lifting water out of there. And we thought we got a really pristine sample of the reservoir, and then the row that I highlight there is the total dissolved solids, 1,600 milligrams per liter. It's a really low number, in fact. That surprised us all. We went out again this year to grab some more sample, and they use a different technique, a swabbing technique. So at this point, they're sending drill string down the well, and they're basically pulling it up, and this pulls the water out of the well, and they pull enough wellbore volumes out, and you take a sample. It should theoretically be representative of your reservoir, or of the fluids that are down in the formation, and much higher value. So repeatability of monitoring, and this is a little bit off topic, but it's certainly something that will be discussed at the conference and is going to be important for CCS in general. Repeatability of techniques, communications with the vendors that are going to be going out and doing your monitoring activities, including groundwater sampling, is extremely important. We're probably going to have to go now take a third sample out here, either going back to one of these two techniques or using a different technique to reconcile these issues. And, it's not so much just important to tell EPA that, hey, we're protecting this water source, although it is, but we need to be collecting samples of this reservoir throughout the injection project and after the injection project to show EPA that we're not impacting the underground source of drinking water. So if we don't know what the baseline is, it's really difficult to make that comparison. So this stuff's pretty important. Some other recent field operations that we've done are an injection fall-off test. You know, I think most folks that have taken a petroleum type geology or engineering class would be familiar with this, but you can determine a lot of properties of your reservoir by doing an injection test and then monitoring pressure during the buildup and then monitoring pressure during the fall off. And if you do it in a step rate fashion, you're stepping up your injection rate in a controlled manner. You should even theoretically get an idea of what the reservoir geomechanical properties are, including the fracture pressure. Well, good news, bad news is this reservoir is so porous and permeable, we weren't able to reach a rate using the diameter of the well that we have here to achieve a parting pressure. You know, even up to a rate that's equivalent in CO2 terms of 3.8 thousand metric tons per day. So we were putting a lot of water into the well. But the good news is you still can determine a lot of interesting properties, including confirming those permeability values that I mentioned earlier. Those came from core data. You know, we're still getting Darcy level permeability in our reservoir. And again, even when we had a pressure of over 2,000 PSI, we didn't part the reservoir. So I guess just to say that another way, you can learn a lot about your reservoir before you inject any CO2 into it if your regulator can give you permission to do a water test and use that as an analog for CO2 injection. Richard's favorite test, one that we did also in the last year, the US DOE funded a controlled source electromagnetic survey that I'll confess I don't know a lot about. But what it would be is you're using electromagnetics as a way to indirectly monitor your CO2 plume dimensions, analogous to repeat seismic. But in this case, they were using a source that was towed by a helicopter that coincidentally, unfortunately, does really look like a lot like a bomb if you could focus your eyes in on that. So Richard got to deal with a lot of cool phone calls. And so earlier this year, they did a flight effectively over the entire storage site with, you know, transmitters laid out on the roads, and you got the receiver in the overhead. And you know, this would be if it could be determined to be effective in CO2 monitoring, would be a small fraction of the cost of seismic. And other than the crazy phone calls you're getting from locals, a lot less, in fact, impact on communities, because we're not putting we're not putting sources out that are going to thump the ground next to someone's house. We're not laying out receivers, et cetera. So just another way to showcase that if you have a friendly site host, that these carbon safe projects are a nice place to showcase emerging technologies. So yeah, they're meant to commercialize CO2 storage, but there's opportunities for scientific widgets and potential transformational technologies to also be demonstrated at these sites. Last thing I'll mention, it may come across as a bit off topic, but just sort of another opportunity that is provided by projects that are funded, at least in the US, by the federal government. And that is, you know, another way to educate the public or educate stakeholders in CCS. So in the last several years, the Society of Petroleum Engineers published a storage resource management system. It's kind of analogous, or very analogous to the petroleum resource management system that some folks may be aware of. That's a system by which you can kind of codify a play or just a region that you see CO2 storage potential and then get up to the point where you have reserves, which is, you know, in the US, that means something that has an economic value, something I could put on my financial statement, something I could sell. And so CO2 storage prospects, now that they have an economic value, as Richard was mentioning, would be a similar situation. And so this project provides an opportunity to educate stakeholders on how a project would move through this CO2 storage resource management system, from something that's a play or a concept. Hey, I think I know this rock is underneath this region, and I think it has porosity, and so you know, it's very prospective. You do a lot of characterization data. You're moving up into that contingent category, kind of that middle category. And then at the end of this project, at the end of this phase of the project, if we have permits from EPA, so permits to operate, and we are going to go forward with the project, which means there's been financial commitment from CO2 sources, storage operator, or it could be also EPA, or sorry, DOE support, or probably all of those together. Then we move to that level of capacity, which again is kind of analogous to reserves. And so this just provides an opportunity. You know, a lot of companies, I'm sure, are going through this process because they would like to have a property. They'd like to say, hey, I've got X amount of capacity. Now that's a defined term. It has a value now in the US. And so we could walk through that process with a CO2 storage project that's federally funded and show people, hey, here, this is how you move through the process. And they'd say, okay, now I realize I probably need to drill a stratigraphic well or two, get my Class 6 permits, et cetera, before I reach that point where I have a bookable capacity value. So just another way that these types of publicly supported projects in the U.S. can benefit the commercial prospects for CO2 storage in the U.S. Those are my slides. I'd like to thank everyone for letting me present again, and I guess we're taking questions as a group later on?
Yeah.
Excellent.